So our nonlinear, first order nonlinear model we're going to talk about is the logistic model. So we've talked about population growth. Our basic population growth model and we've seen this one in other, outside of the context of differential equations in other classes. The change in the population with respect to time is proportional to the population. So population growth, exponential growth or decay, radioactive decay, that's what I meant to say there, we can model with this differential equation. And we know we get an exponential solution here. This is a separable differential equation. We get exponential solution. So we say, in this case, the relative or specific growth rate is, we just divide both sides of this by p, so rate of change of p with respect to t over p, well, that's going to be constant. So in this basic model, that's constant. So our specific growth rate or our relative growth rate is constant. If we make an assumption that our growth rate is dependent on the current population, and the population can vary in time, I'm going to say if this growth rate is not constant, the population does vary in time. If this growth rate varies in time, then we can write that this quantity is some function of the population. So it's dependent on the current population. The relative growth rate is dependent on the current population. Or, just rewriting this, the rate of change of our population with respect to time is a population times this, some function of the population. This is called the density hypothesis. Or the density dependent hypothesis. So just a different model for population growth. So the model that we're going to talk about today is our simplest assumption for the form of this function, other than being a constant, is that it is linear. So we're just going to say f of p equals some c1 times p plus c2. that's going to be our function of our population. If we let f of 0 equals r and f of some value k equals 0, and we call k the carrying capacity, and the carrying capacity is, we could also think of it as the limiting population. So at some value of the population, our growth in our population is 0. We have C2 equals R, and C1 equals negative R over K. So f of P in that case is R minus R over K times P. And our equation, dP dt, is P times R minus R over K times P. And then just to make this easier to write, we let R equal A and R over K equal B. In that case, we end up with dP dt equals P times A minus BP. And if both A and B are positive, we call this the logistic equation. The logistic equation is probably the one of the most prevalent equations for population growth, other than our basic population growth model. And we can think of this term, if we distribute this p, the negative b times p squared, as the inhibiting term. Because it's subtracting from the growth rate of our population. And it describes the effect of things that are detrimental to the population, to the population growth. So overcrowding, lack of food, pollution, waste buildup, that kind of thing. That's what this negative b over p squared has to do with those kinds of things which would limit the population growth. So what I want to do today is talk about the solution to the logistic equation and kind of the behavior of our solution curves in various areas of the plane. And then our homework has to do with the logistic equation and then some variations on the basic logistic equation. So we're spending some time with this because this is, other than the most basic population growth model, it's the second most basic population growth model, and it ends up being applied to a lot of different things. Well, this is separable, so we're going to separate this to solve this. And as we have seen with a lot of other things, The solution to the logistic equation is not necessarily difficult, but arranging it in a nice form just takes a lot of work. So we're going to separate this. So we have dP over P times A minus BP equals dt. Now to solve this, what integration technique are we going to use there on the left-hand side? Partial fraction. So we're going to say 1 over P times A minus BP equals A over P plus B over A minus BP. And we set up our partial fractions. And we end up with, I'm not going to go through the algebra here, but we end up with A equals 1 over A, and B equals B over A. So we have the integral of 1 over A over P plus B over A times A minus BP dP equals, and I'm going to integrate this, we get a T plus C when we integrate the right-hand side. And here, I'm going to say we need to be careful here because this is negative. So when we integrate this, we get 1 over A times the natural log of P. And we're going to assume that this population is positive. Minus, I'm going to use a U sub here. U is A minus BP. So du would be negative 1 over P dP, 1 over B dP. So this becomes negative 1 over A, the B cancels, B from here cancels with this, negative 1 over A times the natural log of A minus BP. And that equals T plus C. I'm going to combine these. So we get 1 over A natural log P over A minus BP equals T plus C. And in our the normal thing that we do here, we exponentiate both sides. I'm going to and I'm going to multiply by A. So we get P over A minus BP equals some constant, we'll call it C1, e to the AT. So I multiply both sides by A and then exponentiate. And we want to solve for P. So I'm going to multiply and gather all my terms that have a P on one side of the equation, everything else on the other side. So I get P plus B P C1 e to the AT equals A C1 e to the AT. So I'm multiplying, distributing this C1 e to the AT, and then gathering all the terms with P on the one side and everything else on the other side. Factor out the P, and I get the population is A C1 e to the AT over 1 plus B C1 e to the AT. And to make this a little nicer and to get it in a little more form that you would normally see it, I'm going to multiply the numerator and denominator by e to the negative AT. So when we do that, we get AC1 over BC1 from this term, and then we get e to the minus at when we multiply the minus at here. So there's our population. Whoops, this should be BC1 plus, not multiplied. So this is our equation. Now I'm going to put in an initial condition. So we're going to let P of 0 be P sub 0. And this is not equal to A over B. So we substitute this, and we get P0 equals AC1 over 1 plus BC1. We substitute T equals 0. And we're going to solve this similarly. We multiply by 1 plus BC1, gather all the terms that have the C1 on one side and everything else on the other side. So we get C1. I'm just going to say this implies that C1, I'm just skipping over some algebra steps here, C1 equals P0 over A minus B P0. Now we're going to substitute. So our population is A P0 over A minus B P0. So we're substituting in here. Over B A P0 over A minus B P0 plus e to the minus at. And these A minus B P0s cancel. And we end up finally with A P0 over A B P0 plus, and I'm finding a common denominator here so I can cancel that A minus B P0, A minus B P0 e to the minus at. So there's some algebra in there, some simplification. It takes a little bit of work. This is what we call the logistic equation. Or sorry, the logistic function. The differential equation is the logistic equation. This is the logistic function. The logistic function basically is just the solution to the logistic differential equation. And this models our population growth when our growth rate is, has some kind of function that's dependent on the population. And we can see as t approaches infinity, our population is going to approach A over B, which is the carrying capacity. So as t approaches infinity, this term approaches 0, and we just get A over B. And as t approaches negative infinity, we see that P approaches 0 because our denominator gets very large. Yes?
Wouldn't it approach 1 over B because there's that A in the numerator and denominator?
Did I do something wrong here? Yeah, the way I've written it, it should approach 1 over b. But let me, I will double check that, just to make sure I didn't make a mistake somewhere in my algebra. So I'm going to put a question mark there for now, and I'll double check on that. Yeah, what did I, let me look back here and see if did I drop an A somewhere?
Shout out Max Webb. That's not a mistake.
Yeah, that's true. I have a negative follower to following.
Follow Maximilian Webb on Instagram.
Yeah, my ratio is negative. If you enjoy it, what I do. Yeah, it's not negative, but it's less than 1. I think I follow like 180 people.
Yeah, I'm not sure what I did here. I probably just made a simplification error somewhere, because it should be, I think this should be A over B, not 1 over B. Yeah, somewhere I got somewhere I got an extra, missed an A or something in here, and I'm not sure where. But I'll go back and look. I know it should be A over B. So we talked about an idea. One of the ideas we talked about in chapter 1 was looking at our equilibrium solutions. That's when our growth rate equals 0. And if we go back here, our equilibrium solution is when the growth rate equals 0. So that's going to be when P equals 0, or when A minus BP equals 0. Those are our equilibrium solutions when the growth rate is equal to 0. And we can look at our typical solution curve in those regions to see what the solution curve looks like. So our typical solution curves this horizontal line is A over B. That's where we get 1. That's one of our equilibrium solutions. And this is P equals 0, our horizontal axis. And we get an inflection point at A over 2B. And we find this by taking our second derivative to look for our inflection points. So if our initial population is below A over 2B, our solution curve, typical solution curve, would look like this. And if we went backwards here, we approach 0. Like so. And if P0 is above A over B, our solution curve looks like this. A typical solution curve. This is P0 here, this would be P0 there. And if P0 is up here, our solution curve, we'd end up with an inflection point here, like so. So those are typical solution curves in the region defined by the equilibrium solutions. You'll have a couple of homework problems that ask you, it says use the phase diagram, I think. Basically, what I want you to do on those problems, what it's saying that you should do, is look at those equilibrium solutions where the growth rate is 0, and then you want to sketch the solution curves in the region, a typical solution curve in the region defined by the equilibrium solutions. The equilibrium solutions, again, where the growth rate equals 0. And for this equation, I looked back to here. The growth rate is 0 when P equals 0, or when A minus BP equals 0. So some variations on the logistic equation. They include, you could include a constant term that we add or subtract. That would reflect immigration or emigration. So population coming in at some particular rate or leaving at some particular rate. So in that case, let me go back to this equation. Here, you'd have a plus H or a minus H that represents the immigration rate. You can have a variable term. You can add or subtract a variable term that reflects a change in the immigration or emigration rate that depends on the current population. So if the population, as the population grows, maybe the immigration rate decreases, something like that. And you have other modifications that can reflect different kinds of growth or decay. So you just add or subtract other terms here, or change this equation from a linear equation to some other kind of equation to represent other kinds of growth and decay. And our homework is just going to have to do with looking at the logistic equation and a couple of basic variations on the logistic equation. All right, questions? Okay.
No examples.
I like the examples.
I do too.
Yeah,
But
obviously from the homework part of it,
And the
because
book-
we didn't have like 10 examples.
this is just like plug and chug, right? Like there's not much.
Yeah, there's not, I mean, we know the equation, we know the solution.
Okay.
Do you have some questions that ask how does this term change things, or typical solution curve? I think there's might be one that asks you to solve a different kind of equation, but it's the same idea as what we did here.
Okay.
Yeah.
Is this on the test? Because I didn't see any like review comments on it.
This is on the test.
It's on
This one section. And this is section 3.2. And I'm going to see where, if